The first alert looked like a cache issue. Cache hit rate dropped below threshold, then another. Database CPU above 90%. Slack followed immediately. Why are we hammering the DB? Latency just spiked across all services. Seeing timeouts everywhere. I opened Grafana. Request rate was steady, nothing unusual, but database queries had exploded, from a few thousand per second to tens of thousands, within minutes. And then the real signal. Cache hit rate, almost zero. Environment context. We were running on AWS, EKS cluster in US East 1, around 85 microservices. Traffic averaged about 3K requests per second. We used Redis as a distributed cache, critical for product data, pricing, and user sessions. Backend database was RDS PostgreSQL. Read replicas handled read-heavy workloads. CloudFront and API gateway sat in front. CI/CD was GitHub Actions and Argo CD. Monitoring stack included Prometheus, Grafana, and tracing. Cache was central to performance. Without it, the database would not keep up. Initial symptoms. Users reported slow responses, then timeouts, then failed requests. From the outside, it looked like a database outage, but the database was still running, barely. CPU was maxed out. Connections were increasing, but the system was not completely down. Some requests still succeeded, which made it harder to diagnose. Cache metrics showed a sharp drop in hit rate. Almost everything was amiss, which meant requests were bypassing cache and hitting the database directly. Investigation and escalation. First thought was cache eviction. Maybe Redis had lost data. We checked. Keys were present. Memory usage was normal. No restart events. So the cache was not empty. Then why were we missing it? We traced a request. Cache lookup, miss. Then database query. Then cache write. That was expected. But the next request, miss again. Cache should have been warm. We looked at TTLs, short, very short. Keys were expiring quickly, but that alone did not explain the spike. Then we noticed timing. Many keys had identical expiration times. They were expiring simultaneously. That was the clue. Now Slack was getting tense. DB is about to hit connection limits. Should we scale replicas? Cache is not helping. We dug deeper. At a specific timestamp, a large set of keys expired, all at once. Root cause. The root issue was synchronized cache expiration. We had introduced a caching layer for product data. Keys were set with identical TTL values, for example, 10 minutes, and they were populated in batches, which meant they expired in batches, at scale. When the TTL hit, thousands of keys expired at the same moment. Requests that depended on those keys all missed cache, and all hit the database simultaneously. This created a thundering herd, no coordination, no throttling, just a surge. Mitigation and recovery. First step was to reduce pressure on the database. We introduced request level locking. If one request was fetching data for a key, others would wait, instead of hitting the database again. Then we added jitter to cache TTLs, randomized expiration times, so keys would not expire simultaneously. Next, we increased cache TTL for critical data, reduced frequency of expiration. We also scaled read replicas temporarily, gave the database breathing room. As these changes rolled out, cache hit rate improved, database load dropped, latency followed, system stabilized within about 40 minutes. Post-mortem reflection. What failed was not the cache, it was how we used it. We assumed uniform TTLs were fine, but at scale, they synchronized behavior. Detection was also incomplete. We saw cache misses, but did not correlate them with expiration patterns. Engineering lessons. Cache expiration should be randomized. Systems must prevent duplicate work under cache miss conditions. Request coalescing can reduce load significantly. Observability should include cache lifecycle metrics, not just hit and miss rates. In the end, nothing new was added, nothing was deployed, but everything expired at once, and that was enough.